This video is brought to you by mywayteaching.com.
In this part, we are going to study about transverse and longitudinal waves. Okay. See, mechanical waves can be transverse or longitudinal depending on the relationship between the directions of disturbance or displacement in the medium and that of the propagation of wave, which means the motion of mechanical waves involves oscillations of constituents of the medium, isn't it? Yes. If the constituents of the medium oscillate perpendicular to the direction of propagation, then we call them as transverse wave. If they oscillate along the direction of propagation, then we call them as a longitudinal wave. Okay. You can see here a single pulse, how it is transmitted, that is sent along a stretched string, a single pulse, and a typical element of string, such as that marked with a dot, moves up and then down as the pulse passes through. The element's motion is perpendicular to the direction in which the wave travels. Okay. So here this shows the propagation of a single pulse along a string resulting from a single up and down jerk. So this pulse moves in this direction, but the oscillations or the disturbance is perpendicular to the direction of propagation. If the string is very long compared to size of the pulse will damp out before it reaches the other end. Okay, and the reflection from that end may be ignored. You can see one more similar situation here. Here the external agent gives a continuous periodic sinusoidal up and down jerk. External agent is giving that jerk to one end of the string, and the resulting disturbance on this string is then a sinusoidal wave. As you can see here, it is a sinusoidal wave. In either case, the elements of the string oscillate about their equilibrium mean position as the pulse or wave passes through them, isn't it? Yes, and the oscillations are normal to the direction of wave motion along the string. So, this is the example of transfer wave, isn't it? Because the oscillations are perpendicular to the direction of this sinusoidal wave. So, this is the quality or this is the property of this transverse wave. See, we can look at a wave in two different ways. We can fix an instant of time and picture the wave in space. That will give us the shape of the wave as a whole in space at a given instant. Another way is to fix a location, that is, fix a attention on a particular element of string and see its oscillatory motion in time. So we can see a wave in two different ways. You can see in this particular figure, a sound wave is set up in an air-filled pipe by moving a piston back and forth. As the oscillations of an element of the air are parallel to the direction in which the wave travels, the wave is a longitudinal wave. So here the oscillation as well as the disturbance both are parallel to each other. So both are moving in the same direction. So this is an example of longitudinal wave. The most familiar example of this longitudinal wave, we can say the propagation of sound waves. That is a very good example. A long pipe which is filled with air, it has a piston at one end A sudden single push forward and pull back of the piston will generate a pulse of condensation and rarefactions. If this push and pull of the piston is continuous and periodic, a sinusoidal wave will be generated propagating in air along the length of the pipe. So, this is clearly an example of longitudinal wave, isn't it? See, the waves that we discussed till now, they are transverse or longitudinal or traveling or progressive wave. Since they travel from one part of the medium to the another, the material medium as a whole does not move. Only the disturbance moves, but not the material medium. A stream, for example, it constitutes motion of water as a whole. In a water wave, it is the disturbance that moves, not the water as a whole, isn't it? Water mass, it remains at the same place as it was before. Only the disturbance moves in the form of circles when we throw a pebble into the water, isn't it? So, similarly, a wind should not be confused with a sound wave, what is a propagation of disturbance in air without the motion of air medium as a whole. The mechanical waves are related to the elastic properties of the medium. Okay, the constituents of the medium oscillate perpendicular to wave motion, causing change in shape in case of transverse waves. That is, each element of the medium is subject to shearing stress. Solids and strings have shear modulus, that is, they sustain shearing stress. Fluids have no shape of their own, isn't it? They yield to shearing stress. This is why transfer waves are possible in solids and strings but not in fluids. Solids as well as fluids have bulk modulus, that is, they can sustain that compressive strain. Since longitudinal waves involve this compressive strain, they can be propagated through solids and liquids. So only we see a steel bar possessing both bulk and shear elastic moduli can propagate longitudinal as well as transverse wave. But air can propagate only longitudinal pressure waves. That is important point. This air can propagate only longitudinal pressure waves. Okay. When a medium such as a steel bar propagates both longitudinal and transverse waves, their speeds can be different since they arise from different elastic moduli. Now let us consider one simple problem based on this. Given below are some examples of wave motion. State in each case if the wave motion is transverse, longitudinal, or combination of both. The first one is motion of a king in a longitudinal spring produced by displacing one end of the spring sideways. The second one is waves produced in a cylinder containing a liquid by moving its piston back and forth. Waves produced by a motorboat sailing in water. Ultrasonic waves in air produced by a vibrating quartz crystal. So, what are the kinds of waves it will produce? This motion of a kink in a longitudinal spring produced by displacing one end of the spring sideways, it is nothing but transverse and longitudinal wave. It produces transverse and longitudinal waves. Okay. And the second one that we just studied before, waves produced in a cylinder containing a liquid by a moving its piston back and forth, that is longitudinal, isn't it? Because both wave and the oscillations move in the same direction parallel to each other. And the third one, waves produced by a motorboat sailing in water. In that particular case, it produces both the kinds of waves, that is transverse and longitudinal. And the final one, that is ultrasonic waves in air produced by a vibrating quartz crystal, that will give longitudinal waves. So these are the different kinds of waves produced in various cases. Okay.